Good morning, everyone. And continuing with the last class where we had left out, and I'm going to start with the Z transforms of certain sequence again. And let me share my screen now. Yes. So now what we had discussed in the previous class, I'll just give a brief introduction about what we had covered previously. So we had covered regarding the Z transform of the positive time exponential sequence, that is the transform of a power n u of n, that would be z divided by z minus a. So where ROC would be the entire z plane except at z equals a. So ROC, that is nothing but the region of convergence is the entire z plane except at z is equal to a. So how to draw the graph of the positive time exponential sequence? So let me take a as any other value like this. So mod z would be greater than mod a, right? So that is the ROC of a positive time sequence. So what I'm referring here, it is for a positive time sequence. I'll come for the negative time sequence later on. So now what I can do here is, this is plus a and this is minus a, and I can draw a circle with radius a, and this is the region of convergence of the z plane. So this is the z plane here. So I have the real part of the complex number and I have the imaginary part of the complex number as the y axis, and the entire z plane is given like this. Okay, so this is how I can write the entire z plane, and the circle what I have drawn is taking z is equal to a. So a units will be taken as the radius, and I have drawn the circle with o as the origin. Okay, so that is the positive time exponential sequence. Coming to the negative time exponential sequence, as I already told you, it's a small recap that I'm doing. It's a negative sequence, exponential sequence to be precise. Negative time exponential sequence. Negative time exponential sequence. Negative time exponential sequence. Okay, so when I have this negative time exponential sequence, I have x of n to be minus b power n u of minus n minus 1. So if I take the z transform of this function, that is x of n, okay, so what I can do here is, I'll be having z transform of minus b power n u of minus n minus 1, which I have taken. So that would be z divided by z minus b. So z divided by z minus b. Okay, so this is the z transform of the given negative time exponential sequence. So x of z, that would be equal to z divided by z minus b. So this function, which is somewhat related to the left hand side sequence because of the negative sign which is there. So the ROC, the region of convergence, we wanted to talk about. So how do you say that the region of convergence for a left-handed side sequence? You can draw it in such a way that you will be having, again, let me take the real part of the complex number and the imaginary part of the complex number which is there. Okay, so now what I can do here is, I can have the z is equal to b circle being drawn. So this is the units, b units, that is there from the origin, and I'll be taking the region of convergence within the circle itself. Okay, so this is within the circle. So any value outside b units will be taken as infinity. Once I put that value, you will be taken this as the infinite. That is nothing but x of z will be tending, it will be equal to infinity. So the summation value should be finite there, right? So x of z, the ROC would be mod z less than mod b. Okay, so the region of convergence ROC for a negative times exponential sequence, that is mod z would be less than mod b. Okay, so that's how you can draw the like conclusion, what is the ROC for a negative time exponential sequence. Okay, now coming to the next one, which is double-sided sequence. Double-sided sequence. Double-sided sequence. So now how I can draw this double-sided sequence is, I'll be given with the positive time exponential sequence and also the negative time exponential sequence there. So once when I have this positive time exponential sequence as a power n u of n, the signal given would be a power n u of n plus minus b power n u of minus n minus 1. Okay, so I have two signals, that is positive time. This one is the positive time exponential sequence. Positive time exponential sequence. Positive time exponential sequence. Then it is negative time. I have the negative time exponential sequence. Negative time exponential sequence. Negative time exponential sequence. So now let us apply Z transform on both the sides. That is Z of x of n, that would be Z transform of the first signal, that is a power n u of n, okay, plus Z transform of minus b power n u of minus n and minus 1. Okay, so this one here would be Z divided by Z minus a. Okay, Z divided by Z minus a, plus this one here would be Z divided by Z minus b. Okay, so in the equation you have to derive it entirely, and then you have to say it is Z divided by Z minus a, and this one would be Z divided by Z minus b. So we know certain formulae. I am writing it directly. For your convenience, you have to derive it again, and then you have to come to a conclusion whether the Z transform whatever I have written is to be verified. Okay, now when I talk about the next one, which is the region of convergence, right? So the region of convergence, okay, Z of x of n. If I want to talk about the region of convergence, I have Z transform of a power n u of n, okay, plus Z transform of minus b power n u of minus n minus 1, that is there. So you have Z divided by Z minus a plus Z divided by Z minus b. So this ROC, so I have two ROCs here. So ROC 1. So what is the ROC 1 here? So mod Z would be greater than a. Okay, mod Z would be greater than a. So this one I have ROC to be mod Z less than b. So if I have two ROCs, ROC1 and ROC2, the overall ROC, the overall region of convergence, overall ROC is given by the intersection of two ROCs. Okay, so what I can do here is, generally if I have two signals which are present there, so if I want to find out the overall ROCs, I can take this as one of the important points. You can note it down. And this overall ROC is given by the intersection of two ROCs which are being present here, right? So now if I want to talk about these two ROCs, so mod Z would be greater than mod A, intersection, okay? So intersecting mod Z less than mod B. Okay, mod B, I can write it as mod B here. So now if I want to change this, I can have mod A, okay, to be less than mod Z. Okay, so overall ROC, overall region of convergence is given by okay, mod Z less than mod B less than mod A. Mod Z less than mod B, okay, mod A less than mod Z. So this is the overall ROC. This is the overall ROC. Okay, so this is how I can draw the overall ROC here. So the overall ROC can be represented as the annular section of the intersection of two ROCs. annular section of two ROCs being intersected or intersection of two ROCs. So to draw the ROC, I can write it like this. I can have Z is equal to B here. So this is A and this is minus A and this is the Z plane, the entire Z plane what I'm talking. So this is B and this is minus B, and I can have imaginary part of Z and this one is the real part of Z. Okay, so this would be the region of convergence. This would be the region of convergence. So this is the ROC. Okay, so region of convergence, which is there. So annular section of region of convergence. Okay, so this is the entire ROC which is present here, right? So this is how I can certainly tell about the region of convergence, which is nothing but the annular region, the annular section of the region of convergence of two different signals being added together. That is nothing but the double-sided sequence. For a double-sided sequence, in the problems which you have any integers being given for A and B, you can certainly take it and draw a conclusion that for a double-sided sequence, ROC is the annular section. Okay, so I can draw this to be the region of convergence. I hope all the things are clear to you, and this is how we can draw the conclusion for ROC of a two-sided or a double-sided sequence. Okay, now let me move on to certain properties which are related to the Z transform. Okay, so properties of Z transform. I think all the properties are quite simple, and no need to see to it that there is no longer process or something like that which is involved, and we can certainly come to a conclusion that all the properties that we had discussed in signals and systems is quite simple then. Okay, so let me talk about the linearity property first. Okay, first one is the linearity property. Okay, so let me take two signals here, that is x1 of n and x2 of n. I can take its Z transform. I can take this Z transform of x1 of n, and I can take this one to be Z transform of x2 of n. Okay, I can call this to be x1 of z and this one to be x2 of z. Okay, so now if I have the sum of these two signals there, constants associated with it, say a x1 of n plus b x2 of n. Okay, so this might be one of the signals or the weighted sum of the inputs or to any discrete system that is present there. Now if I want to apply the Z transform, that is a x1 of n plus b x2 of n. So what I can do here, x1 of x2 of z. Okay, so x of z would be equal to a x1 of z plus b x2 of z. So So here I can verify the linearity property which is present there. Okay, so next one, if I want to go to the next thing, which is nothing but the time shift or the translation. I have time shift or translation. Okay, translation, which is nothing but a shift in the time. So either it might be an advanced shift or a delayed shift. So we generally use the term shift or time shift to be precise. I can call this to be the translation of the signal, translated by such units. Okay, so now if I want to talk about the translation of two signals which are being present there, and I can call, say, z transform of a signal to be x of n, I can have it to be x of z. Okay, so now the translation is being done for a delayed signal x of n minus n naught. So it would result into z power minus n naught times x of z. Okay, so what you are going to do, you are going to have z transform of the signal x of n first. Next you are going to find out z power minus n naught multiplied with x of z. Okay, so now this is how you can do it for the time shift or the translation signal which is present there, right? So next one, what I'm going to do here, I need to verify whether the formula that I've written is right or wrong. Okay, so to recall the z transform of a discrete signal, say x of n, I have x of z. Now that is nothing but the summation n would be equal to minus infinity to plus infinity x of n z power minus n. So this x of n would be replaced by x of n minus n naught. So n would be equal to minus naught z power minus n. Okay, so now this entire term n minus n naught, I need to replace it by a single variable. So let m is equal to n minus n naught be a single variable. Be a single variable. Okay, so now what I can do here is sigma, I need to replace it with m here, right? So now n, I can replace it with x of m here, and I can have z power minus n. Okay, so minus n I can recall with, say, n would be written as, okay, n would be written as m minus n naught. Okay, m minus n naught. So z power minus n, if I want to write it as minus n, that would be n naught minus m. That would be, that's how I can write it for x of m, the new variable what I have replaced here. So now if I want to have n, okay, if I want to have n here, so that would be yes. So now if I want to have n, okay, so if I want to replace it by m here, okay, so m would be n minus n naught, what I have written here. So once when n is equal to minus infinity, m will also be equal to minus infinity, and here it would be infinity only. The same limits holds good. So m will be equal to minus infinity to plus infinity. Okay, so now if I have m is equal to minus infinity to plus infinity as the limits of the given summation, I can have sigma, that is m equals minus infinity to plus infinity x of m z power, okay, z power, let me take minus sign common, z power m minus n naught. Okay, so that is there, and I can have z power minus n naught to be taken as the common factor. I'll tell you why, and I can rewrite this equation again. So sigma m would be equal to minus infinity to plus infinity x of m z power, okay, z power minus m plus n naught. Okay, so I can take out sigma, say m equals minus infinity to plus infinity x of m z power minus m z power minus n naught. So if I can keep these two things, and I can take this one as the common factor, like somewhere outside the summation, I can have m to be equal to minus infinity to plus infinity x of m z power minus m with z power minus n naught being multiplied. So that would be for x of z here. So this entire function would be x of z. So I need to multiply with z power minus n naught there. So z of x n minus n naught, that would be equal to z power minus n naught x of z. Okay, so that's how I can recall the translative property or the translation of a given discrete time signal. Okay, the discrete time signal, the discrete time signal, the discrete time signal when translated, when translated, when translated is given by a z transform of the signal, that is x of n minus n naught, that would be equal to z power minus n naught x of z. Okay, now similarly, if I have z of x of n plus n naught, okay, so x of n plus n naught, so what would be the signal here? So if I have, I can change this as x of n minus n naught. Okay, so this minus n naught will be replaced here, which is nothing but z power n naught x of z. Okay, so this is how I can call it for x of n plus n naught. So this signal x of n plus n naught will be the advanced signal between, it is the advanced signal. Okay, this one would be the delayed signal. This one would be the delayed signal. Okay, you have to practice more and more of it to gain a good understanding of certain properties which are there, and I can certainly say that it's ROC which is less within the limits itself. Like, so it would be from within two limits which is present. So it might be any other signal which you can apply. So this z transform can be applied to any of the signals which are continuous, not continuous, it is for a discrete time signal there. So next I have the multiplicative property which is there. So to highlight the ROC, which would be mod z, which will be less than Rx plus less than Rx minus. So somewhat like this, you will be having the region of convergence for it. Okay, so let's stop here. In the next class, we'll come across the multiplication of exponential signal and convolution property also being discussed, and certain sinusoidal sequence and useful signals we will deal in the next class. Okay, so meanwhile, let me stop the class here, and we can have our discussion in the next class.